Okay, so this is going to be a set of notes on what are going to be called the comparison test. And later the limit comparison test, which is like a close cousin to the comparison test here. All right, so we have a comparison test for convergence, and we have one for divergence. Okay, so in the convergence test, I have to start with B sub n as a convergent series. So I know that this one is convergent. Okay, and I have that the sequence an is always positive, and it is always less than or equal to some sequence bn. Okay, so these are both positive sequences, and this one, the bn sequence, dominates the an sequence at every value of n. If that's the case, then any sequence, any series that is dominated by a convergent series will itself be, so this implies that this is convergent. Okay, so this opens up a whole bunch of doors for us, because we have ways to find convergent series. We can do it with geometric series, we can do it with p series, we can do it with, some alternating series. So if I can dominate the series that I have by one of those, then I can prove that that series will in turn converge. So this actually works the other way as well. If Bn diverges, and this inequality goes the other way, right? So 0 is now less than or equal to B sub n less than or equal to A sub n. So now my unknown series is dominating the known one. If that's the case, if I am dominating a known divergent series, then I have to also be divergent. Basically, if I'm dominating something that's going to infinity, I'm going to infinity too. It's kind of how this works out. So let's give an example of how this gets used and how it gets us many more series that we can determine the convergence or divergence of. Okay, so we're going to test the convergence of a particular series, namely the sum from n equals 1 to infinity of 5 over 2 to the n squared plus 4 to the n plus 3. Okay, we want to know if this thing converges. All right, so if I look at this, 0 is less than or equal to this thing. For all n greater than 1, 1 or bigger, this thing is always positive, right? So that thing is always positive. And 4n is going to be positive, and 3n is going to be positive. So both of these are making the denominator smaller. So this has to be less than or equal to 5 over 2 to the n squared. And since 5 halves is greater than 1, this is going to be greater than or equal to 1 over n squared for all n. Now, why did I do this? Because now I've showed that this thing is being dominated by the p series 1 over n squared. And we know that the series 1 over n squared, 1 over n squared converges, because this is a p series, and p is bigger than 1. So that's going to converge. So that means my series is dominated by a convergent series, which implies that my series from n equals 1 to infinity of 5 over 2 to the n squared plus 4n plus 3 will in fact converge. All right. So that's a simple use of the comparison test to show convergence. Now let's give an example of where it will show divergence. Okay, so let's take a look at the sum from the square root of n over n minus 1, and does this converge? Okay, so here's what I play with this. If I take this guy, this one, for 1 and greater, right? So this actually is going to have to start a little bit larger, right? Because this can't exist when n equals 1. So let's say this is n equals 2 to infinity. There we go. So for 2 and greater, this thing is going to be positive. So this thing is always greater than 0, right? So let's go the other way here, though. I want this thing to dominate something. So I'm going to examine this kind of working the other direction. Got that. That has to be bigger than square root of n over n, because if I'm making the denominator smaller, then the whole thing is bigger, which this is actually equal to 1 over n to the 1/2. And all this is going to be positive when n is 2 or bigger, right? So let's take a look at what's going on here. That's a p-series, right? So this thing, n to the 1/2, that's a p-series. This is p-series. So this diverges, right? This diverges because this is a p-series where p is less than or equal to 1. So I get divergence. This is dominated by my series. So if my series dominates a divergent series, then this means that my series must also diverge. Okay, so this is kind of like the exact opposite of the last example. Instead of being dominated by a convergent series, I am dominating a divergent series, which means that I, in turn, diverge. Now, there is a problematic case here. Okay, so I have a problem child. So let's say I have the sum of 1 over 2 to the n minus 1. All right, it would be great if I could compare this to the sum of 1 over 2 to the n, because that's the sum of 1/2 times 1/2 to the n minus 1, and that is geometric, and we have the absolute value of r being 1/2, which is less than 1, so this converges, right? So now let's try to compare these, right? So 0 less than or equal to. Now, which one is the bigger one? Well, in fact, 1 over 2n is going to be dominated by 1 over 2 to the n minus 1. And that's exactly the wrong thing I want. Because if I have convergence, I want the convergent series to do the dominating. Here, I have the convergent series being dominated by the other one. So this means that the comparison test does not apply here. We don't meet the conditions of the comparison test. It's so close, but it won't work. Okay, so this brings us to the stepchild of the comparison test, which is what we call the limit comparison test. Okay, so the limit comparison test is a little bit different, okay? It says that I have two series, n, bn, and that these are always positive. So an and bn are always greater than 0. All right, if I have that, then I'm going to take the limit. And I'm going to take the limit as n approaches infinity of an over bn. And if that limit gets me to a constant which is not infinity, then either both an and bn converge, or both sum of an and sum of bn diverge. So these are my two options. Either they both converge or they both diverge if the limit comes out to some constant. If it goes off to infinity, I've got nothing. But if it comes to a constant, both series have to be either converging or diverging. So the limit comparison test is not broadly used. It is used specifically when you do the comparison test and it doesn't apply in the situation like we did before. So before we were testing whether or not the series of 1 over 2 to the n minus 1 converges. And the comparison test failed on us. But we know that the series from 1 over 2 to the n converges because it's a geometric series with 1/2 as r, which is less than 1. Okay, so what we do is we build our limit. We take the limit as n approaches infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. This becomes the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. And these are the two fastest terms. They're equal, so this thing is going to 1. 1 does not equal infinity. So this means since this converges, we now know so does the other one. And I'm done. So this is my workaround for when the comparison test doesn't work. The comparison test is really fast, but the limit comparison test will work in those cases where the comparison test kind of leaves you hanging. All right, so let's look at another one, and let's look at one where it diverges. Okay, so let's test the series where we have 2 to the n squared plus 3n over the square root of 5 plus n to the 5th. Erg. Okay, no idea what to do there. So let's do some thinking here. If I have just the two fastest terms, right? So I have the the 2n squared up top and the n to the 5/2 in the bottom, right? N to the 5th square root. All right, so a little bit of manipulation here. That's going to give me 2 over n, let's see, 4/2, 5/2 puts 1/2 in the bottom. This is 2 times the series 1 over n to the 1/2. This is a p series where p is less than or equal to 1, which means I diverge. Okay, so now I just have to build the limit and do the comparing, right? So let's take the limit as n approaches infinity of a sub n, so that's going to be the 2n squared plus 3n over square root of 5 plus n to the 5th times this guy, right? So this is going to be, what's this? This is n to the 1/2 over 2, so we're going to flip that over. It's n to the 1/2 over 2 because we're dividing by it, which means we're multiplying by the reciprocal, right? A little bit of manipulation here. Let's see, I now have, well, let's see, 2 plus 1/2 is 2n to the 5/2 plus 3n to the 3/2 over 2 times the square root of 5 plus n to the 5th. But this n is to the 5/2. This n is to the 5/2. Those are the two fastest terms. They both have a coefficient of 2. So 2 divided by 2 makes this, oh, this should be, yeah. So this 2 divided by 2 is going to make this equal to 1, which is not infinity. So if this ratio works out to be 1, this one diverges, which means that the other one must also diverge. Okay, yay, limit comparison test. All right, so Comparison test tells me that if a convergent series dominates my series, then my series must converge. If my series is dominating a divergent series, then my series must diverge. And when those tests don't quite exactly work, what I can do is I can take the two things I want to compare and build a ratio of them. Take the limit as n goes to infinity, and if I get a constant, then they either both converge or they both diverge. All right, so there's your comparison test and your limit comparison test.